Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 11.7 from your textbook, which is a summary of everything we've discussed so far about infinite numerical series. In the first part of our video here, we're going to be just going over a couple basic things to sort of remind you about sequences and series. Remember, most of our attention has been focused on series, from 11.2 all the way up to where we are now in 11.7. But of course, all series are based on sequences. So in this first part of this sort of summary here, we're not going to introduce any sort of new concepts. We're just going to do a quick review of making sure that we understand some of the similarities and differences between discussing the behavior of sequences and discussing the behavior of series. So before we get into sort of our big set of examples, which is going to really just sort of walk us through all the different sort of situations that we might encounter, what I'd like to do is just make a couple notes here about why we're going to go over the set of examples that we're going to discuss here. So the couple notes that I really want you guys to be thinking about as we go through this is, first, make sure you understand the difference between converging and diverging as a sequence and converging and diverging as a series. So we really want to distinguish, as we do these examples, what it means to converge or diverge as a sequence and what it means to converge or diverge as a series. Remember, a sequence is simply, as its name would imply, a sequence of those values. So talking about where those are converging or diverging is talking about where are those values headed. A series is summing up a sequence. So when we talk about that converging or diverging, we're not saying where are the terms headed, we're saying where is the sum of those terms headed. The second thing to sort of keep in mind as we do this is that we have introduced a whole variety of ways of testing the behavior of a series. We have things from the very start like the integral test, the direct comparison test, limit comparison test. More recently, we've learned the ratio and root test. We have the alternating series test. All those things, those tests, are for series. All of them relate to the behavior of series. For sequences, we don't use tests to analyze them. Instead, for sequences, we simply look at their limit. So just remember that all these tests we've been discussing, they apply to series. For the behavior of sequences, we're just analyzing the limit. Finally, the other thing that we're going to be sort of discussing here is making sure that we understand the difference for series, because again, for sequences, we just have convergence or divergence. But for series, we talked about two different types of convergence, absolute convergence and conditional convergence. So we'll discuss that a little bit. Okay, so with these things in mind, let's take a look at a set of examples. Now, these examples are not going to be ones that are computationally very challenging. In fact, every one of these we should pretty much be able to do in some ways just in our head. But in what our main purpose is here is just to make sure that we really understand what is the sequence component, what is the series component, and what are their behaviors, just to really make sure we're good with all this foundational stuff. Then, in some of the later videos for this summary, we'll go ahead and we'll actually sort of review the specific computational techniques, how to perform all these different tests, all that sort of stuff. But right now, we're just trying to summarize these different terms and these different behaviors. All right, so we've got a whole set of examples here that we're going to go through. All of them are relatively simple, but what I'd like to do with each of them is discuss a little bit about the corresponding sequence, then talk about the behavior of the sequence, then talk about the behavior of the series. So if we think about this first one here, we're summing up from n equals 1 to infinity, n. So the sort of corresponding sequence, a sub n, would of course just be n. And the terms of that, if we think about it, would be things like 1, and then 2, and 3, and 4, and so on. If we think about that, right, that's what the sequence looks like. This infinite series then, of course, this sum n equals 1 to infinity n, well, it doesn't equal these values. It equals the sum of these. So it's 1 plus 2 plus 3 plus 4 plus dot, dot, dot. So while the sequence continues out discretely for each of these values, the series also continues summing those up. Okay, now what can we say about the sequence here? So let's talk about the sequence. So the sequence, a sub n, well, there should be no sort of difficulty here. Where is this sequence headed? It's going to diverge to positive infinity. This a sub n is headed towards positive infinity. So this diverges. Okay, now Since this sequence is diverging to positive infinity, what are we doing in this series? Well, we're adding things that get larger and larger, and we're trying to add them all together. So the series is also going to diverge. And we would know that formally through something like the test for divergence, because this limit is headed towards positive infinity, which is not 0. So we also know the series sum n equals 1 to infinity n diverges. Also technically to positive infinity, because we know we're adding up an infinite amount of these larger and larger positive terms. Okay, so this first one, not particularly interesting. This is just an example of where the sequence diverges and the series diverges. Of course, if the sequence diverges, then the series must diverge. Why is that? Well, test for divergence. Remember, the test for divergence gives us a very strict limitation for when the series even has a chance of converging. For the series to converge, the limit must be 0. Even if the limit is 0, the series still might not converge. But if the limit of the sequence is anything else, in this case, it diverging, then that automatically means the series is going to diverge. All right, let's take a look at our second one here. And the second one is an alternating sequence, or in terms of the series, it's an alternating series. So let's look at the corresponding sequence. Well, it's minus 1 to the n. And since we're starting from n equals 0, the first one would be minus 1 to the 0, which is 1, and then minus 1, and then 1, and then minus 1, so on and so forth. And of course, the sum would be taking 1 plus minus 1 plus 1 plus minus 1 plus dot dot dot. Okay, so what can we say about the sequence here? Well, the sequence is just oscillating between 1 and minus 1. It's not even tending to minus 1 and 1. It already is just always at 1 or minus 1. So we know that the sequence a sub n diverges. Actually, its limit simply does not exist, right? And that's because it's oscillating between plus minus 1. Okay, once again, we immediately know the behavior of the series. From test for divergence, we know that if the sequence diverges, then the series automatically diverges as well. Remember, if the sequence goes anywhere but 0, the series automatically diverges. So in this case, the series sum n equals 0 to infinity minus 1 to the n diverges. Now, we should be a little careful here. This is our first sort of subtle moment. While the sequence is obviously oscillating between plus or minus 1, does that mean that the series is? Well, not really. I mean, if you imagine adding these up, you would actually have 1, then you would add minus 1, and you'd have 0. And then you'd add 1, and you'd have 1, and you'd add minus 1, and you'd get 0. So really, the sum seems to oscillate between 0 and 1, because it depends on if you're on an even or odd sum. So again, just because this guy diverges doesn't mean that this diverges in the same way. We just know that if this diverges, then this one diverges. Now again, we're not usually very interested in if something diverges, where does it diverge to? So we'll just leave it as diverges. So my first two examples are just there to remind you that if the sequence diverges, then the series must automatically diverge. It's also here to remind you that diverging can mean many different things. Here we saw something because it was diverging to an infinite value. Here we saw something that was diverging because the limit simply does not exist, namely due to that oscillatory behavior. Okay, let's look at this third one. We have the sum from n equals 1 to infinity, e to the 1 over n. Let's talk about the corresponding sequence. So that would be e to the 1 over n. So since we're starting from 1, that looks like it would be e to the 1/2, e to the 1/3, e to the 1/4, so on and so forth. And of course, the sum would be doing e plus e to the 1/2 plus e to the 1/3 plus e to the 1/4 plus dot dot dot. Okay, so let's talk about where the sequence is headed. So the sequence, a sub n, well, as n gets larger and larger, 1 over n is going to get smaller and smaller. It's going to approach 0. And e to the 0 power goes to 1. So the sequence here converges. Well, we can actually write it this way. The sequence a sub n goes to 1. It converges to 1. So the sequence is converging to 1. These values, as you go further and further, are getting closer and closer to 1. You can try that if you want. You can take a value really large, n equals 100, n equals 1,000. E to the 1 over n is going to be really close to 1. So the sequence is converging to 1. What does that tell us about our series? Well, test for divergence again. This limit is headed to 1. 1 is not equal to 0. That means the series automatically diverges. So the series, sum n equals 1 to infinity, e to the 1 over n, diverges. We actually know where it's diverging to. It's going to positive infinity. How do we know that? Well, these have always positive terms, and if you think about what's really happening, these terms are getting closer and closer to 1. So in the long run, what you're doing is you're adding up an infinite amount of 1s, and an infinite amount of 1s is still going to be infinite. So now we saw something where the sequence converged, but the series still diverged. So actually, in these first three situations, while the sequence might be pretty interesting, the series isn't even really interesting to us, because here we were adding up things that got larger and larger. Here we were adding up things that weren't even headed to a particular place. And here we were adding up things that were headed to some finite value, but we have an infinite amount of them. So it doesn't make sense to try to add them up. Okay. And now we're ready to move into the ones where things become a bit more interesting, the ones where we actually have to analyze the series a little bit more carefully. And number 4 here is one we've encountered many times. It's the harmonic series. So the sequence here, of course, the corresponding sequence, a sub n, is 1 over n, and it has terms like 1, then 1/2, then 1/3, then 1/4, so on. And of course, the series is trying to sum all those up. 1 plus 1/2 plus 1/3 plus 1/4 plus ... Okay, where is this sequence headed? Well, if the denominator is getting larger and larger and the numerator is always 1, well, we know the sequence, a sub n, is headed to 0. It converges to 0. Okay, so we have our first one where the sequence is converging to 0. So test for divergence gives us no information. Does that mean that the series converges? Well, no. We know that this harmonic series, as a p-series with power equal to 1, still diverges. We actually proved that using the integral test. So this series still diverges. So the series sum n equals 1 to infinity, 1 n, diverges. Where is it diverging to? Well, it's actually diverging to positive infinity still. How do we know that? Because we're adding up more and more positive things. Now, we only know that it's diverging because we actually went ahead and did that integral test. But since it's diverging, we now know it must be diverging to positive infinity because all these terms are positive. I realize back here, I missed writing this in, e 1 over n there and 1 over n there. Sorry, forgot to fill those guys in. Just bad notation there. Didn't miss it up there. Okay, good. So the harmonic series is a really, really important one because it's an example where the sequence is headed to 0. The terms are getting infinitesimally small, but when you try to sum them up, their sum is still getting infinitely large. And that's because the speed at which 1 over n converges to 0 isn't very fast, right? These terms, while they're headed to 0, don't go there very quickly. That's why this series still diverges. Okay, now let's go ahead and look at one level further, 1 over n squared. Now this one, we know here, a sub n is 1 over n squared. And the terms here are 1, and then a quarter, and then a ninth, and then a 16th. And of course, the sum, or the series, is 1 plus a quarter, plus a ninth, plus a 16th, plus ... Well, once again, it should be no doubt that the sequence, a sub n, goes to 0. It converges to 0 for sure, right? I mean, again, numerator is not changing, but the denominator is getting larger and larger. But this time, this series, sum n equals 1 to infinity, 1 over n squared, actually converges. Now, with this, again, we did as a p-series. We also proved this using the integral test. We know that that sum, n equals 1 to infinity, 1 over n squared, converges. Do we know what it converges to? Well, mathematically, yes. Mathematics does know what this converges to. But we never discussed that in our class because, again, summing up series is actually pretty challenging. This series actually sums up to pi squared over 6. And it's actually a very challenging sort of problem to actually show that that sums up to that specific value. But what's important for us is that we know that this thing does sum up to a finite value. We know that this series, even though it's a sum of an infinite amount of things, does actually converge to a finite value. All right, what else can we say about this? Well, we can actually specify the type of convergence here. Since this has always positive terms, we know that since it converges, this is an example of something that is absolutely convergent. Because obviously, if I put this in absolute value, it doesn't change anything, so I know that this still converges. It's absolutely convergent. Okay. So why does this one converge as opposed to this one that diverge, even though they both have a sequence that's set it to 0? It's all about the speed. 1 over n squared collapses down to 0 much more quickly than 1 over n. And that's why when we try to sum up those infinite amount of infinitesimally small things, well, that infinitesimally small component wins out and we're actually able to sum it up. Okay, now let's change gears a little bit and talk about some that aren't always positive. So let's look at 6 here. This is the sum from n equals 1 to infinity, minus 1 to the n, 1 over n. This is what we sometimes reference as the alternating harmonic. So the terms here would be minus 1 to the n, 1 over n. And if we look at those, well, since we're starting at n equals 1, we'd have minus 1, then we'd have positive 1/2, then minus 1/3, then positive 1/4, and so on. The actual series would look something like this. It would be minus 1 plus 1/2, minus 1/3, plus 1/4, minus ... right? Because the next one would be minus 1/5, so on and so forth. Now, as a sequence, well, sure, these are alternating. They're oscillating between positive and negative, but their magnitude is getting smaller and smaller. When you analyze an alternating sequence, you put it in absolute value, and if the limit goes to 0, well, then we know that the alternating sequence converges. And that is true here, right? That in absolute value definitely goes to 0, so we know that the sequence a sub n is headed to 0. It converges to 0. Right, because what's happening here is, you'll have to excuse sort of the ugliness of it, but just to sort of fill it in there, what we're really doing is we sort of have here, and then here, 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 right? What's going on is that even though it's hopping between negative, positive, negative, positive, negative, positive, so on, it's tightening around 0, so it still is converging to 0 as a sequence. Now, what about as a series? Well, if you use the alternating series test, this limit is 0, and the terms are strictly decreasing, so it converges. So the series sum n equals 1 to infinity minus 1 to n, 1 over n, converges. Now, what type of convergence is that? Well, if we put this thing in absolute value, we wouldn't have that minus 1 to the n, and we'd be back to our standard harmonic, which we know diverges. So this is your sort of prototypical example of something that is conditionally convergent. This series does converge. This is summing up to a finite value. But the only reason that it's summing up to a finite value is because these terms are sort of having partial cancellations with each other. Minus 1 and then a positive 1/2. Minus 1/3, but then a positive 1/4, right? There's these sort of partial cancellations between the positive and negative terms, which means that even though the terms themselves aren't collapsing to 0 that quickly, once you have those cancellations, they collapse a lot faster. So this is an example of something that converges, but only because of that presence of that minus 1 to the n. That's what we call conditionally convergent. All right, the last sort of basic one of these I want to mention is this one, the sum from n equals 1 to infinity minus 1 to the n, 1 over n squared. Here, the terms are, again, this, so they're going to be alternating. Looks like they'd be like minus 1, then positive a fourth, minus 1/9, positive 1/16. And of course, the series would look similar. It would just be summing up those terms. So minus 1 plus a quarter minus a ninth plus a 16th, so on and so forth. Now again, the sequence, there should be no doubt a sub n heads to 0. It converges to 0. Same idea here. Why does the sequence converge to 0? Well, you start off down here, then you're here, then you're here, then you're here, here, right? It tightens along that 0, even though it keeps switching between positive and negative. The series, on the other hand, well, the series, sum n equals 1 to infinity, minus 1 to the n, 1 over n squared. Same thing, alternating series test. These terms go to 0. We just confirmed that. These terms are strictly decreasing. That's clear. It converges. Now, is this one conditionally convergent? Well, if you put the absolute value around it, you'd be back to here. And that is convergent, right? We know that in absolute value, this one would still converge. Now, does that mean that this series equals this series? Absolutely not. This one is much smaller. You can see that. This one's adding up a bunch of positive numbers. This guy's got to be positive. This one, at least the way I wrote it out, has actually got to be negative because the negatives are always bigger than the positives. So this guy converges in both absolute value and normally. So this would be absolutely convergent. Now, this is a different series than the one we did here, but its behavior is absolute convergence. Okay, so the point of these quick 7 examples is, again, nothing really about the test. I mean, I briefly mentioned tests for divergence and briefly mentioned alternating series tests, but the real point is just to make sure that you guys can delineate between discussing the sequence and discussing the series. Notice that in the first set, yep, there were interesting things to say about the sequence, going to pos infinity, diverging because of oscillation, converging to 1. But in all those situations, as soon as that happened, we immediately knew that the series diverged. Then, starting from 4, we got into the ones where the series was more up in the air. The sequence always was going to 0, but the series could exhibit a bunch of different behaviors. That's because it's a necessary condition for the sequence to go to 0 for the series to converge, but it is not sufficient. Just because the sequence goes to 0 does not necessarily mean that the series converges. We saw 1 where the sequence went to 0, but the series diverged, and then we saw 3 where the sequence went to 0, but the series had some behavior of convergence, either absolute convergence or conditional convergence. We also briefly discussed in this idea of the speed at which something converges. That's why this one here diverged, but this one here converged. That idea of the speed, right now everything was just polynomial in nature, so that we know for P series, that power is less than or equal to 1, then it'll diverge. If that power is greater than 1, it'll converge. We're going to investigate the speed of these sort of functions, which we've already sort of hinted at when we've done like a limit comparison test and talked about dominant terms in our next video for this summary. So in this one, we mostly just wanted to sort of study making sure we had all that terminology down. Next, we're going to discuss a little bit more about the speeds of these different sequences and series.